Hello, everyone, and welcome back to part two of probability distributions, so lesson 12.4. So today we're going to learn about what binomial experiments are and how to calculate binomial probabilities and more about probability distributions. So how do I list all the events that could happen and what's the probability of each event? And then we're going to use those to make some calculations. So we'll start like normal with a warm-up. Okay, I want you to write the theoretical probability distribution of flipping a fair coin 3 times and how many heads are going to show up. Okay, remember, all of the probabilities together should always add up to 1 to check, see, did you count all of the events? Go ahead, pause the video, write down the probability distributions of each event occurring, and we'll check your answers. Okay, so something that I might have done, and this might help you for a hint if you haven't finished quite yet. Okay, I like to write down what could happen. And since these are 50-50, okay, 50% heads, 50% tails, you could have heads, 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 and heads, tails, heads, and heads, heads, tails. I would list all of the outcomes. And since there's 2 outcomes that could occur at each spot, okay, I have 2 times 2 times 2. I know I have 8 outcomes. So hopefully you didn't forget any of the 8. Sometimes people do. So the probability of 0 heads is tails, tails, tails. There's only 1 out of the 8 ways it could happen. For one head, I could have a head first, I could have the head second, I could have the head third, as long as it is in one of those 3 spots. Okay, it's probably one head is 3/8, probably 2 heads. There's also the probability of 1 tail, so these are symmetrical. And then once again, probability of 3 heads is heads, 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 only can happen once. And those add up to 1 whole. And this is what the graph would look like for a probability distribution. Okay, there's about a 12.5% chance that there's 0 heads, so this is a little bit above 0.1. 1/8 is 0.125, so that's why these graphs are in decimals. They could be in fractions here as well. And all 4 of these distributions, well, all 4 of these probabilities should add up to 1, and they do. So if we flip 3 coins, we're most likely to get 1 or 2 heads. Not all heads, not all tails, somewhere in the middle. Now, flipping coins is a good example of a binomial experiment. So we're going to learn about binomial experiments today. A binomial experiment has a fixed number of trials. So we're going to repeat something a certain amount of times. Each trial has 2 outcomes. We have a success and a failure. Now that does not mean that we can't have something that can have 4 options. We just have to decide what is success and everything else is failure. So for example, if I roll a die, I could say that the number 1 is a success and everything else is failure. The results of the trials have to be independent, which means second trial has to have the same probability of success as the first trial, and same thing with every other trial. Okay, so each event can't change the outcome of a future event. And in the example I just gave, okay, let's say we roll die 5 times. That means I know I have 5 times that I'm going to do it, and success is roll a 1. We're going to see as we go through this, we want the probability of success, which we are going to call P, is 1 out of 6. And then we're going to learn that we call not success or failure, however you want to describe it, is 5 out of 6. So you can only have 2 things. I either roll a 1 or I don't roll a 1. And this is where the complement comes in. I do an event or I don't, or I do not do an event. So here's an example. I want you to look at this and decide, is this an example of a binomial experiment or is it not? Think, does it fit in all the criteria? If it breaks even one rule for the binomial experiments, then it's not. So go ahead, write this example down. Think, is it binomial? justify your answer, pause the video. When you're ready, unpause it. We'll go over the answers. Okay, so it says spinner is equally likely. Okay, every time I spin it, it seems kind of random chance. So I would say yes, it's a binomial experiment. Okay, we either have success, which is go forward 2 spaces, or failure, anything else. I don't care that there's 4 or 5 other options in the failure space. Okay, I've defined what I want to be success, and everything else is not. And it says each spin is independent, so I'd consider this binomial experiment. Here's another one. There are 7 students in a class, 23 students taking French. You're going to choose a student at random, and then a second student at random. Okay, we're going to choose a student, and then from everyone else, we choose another student. Success is choosing a student who's taking French. Let's see, is it binomial? You go ahead, make your justification, pause the video. When you're ready, unpause it, and I will give you my explanation. Okay, so in this case, not a binomial experiment because the probability of success is changing. From the first student, I get 7 out of 23 possible successes, and then the second one is 6 out of 22. Because this one says that it's got to be a second student, can't be the first student again. So as soon as I'm dealing with situations where I'm not replacing something or the probability is changing every time, that's not binomial. It's not going to help us in the next formula we're going to use. Okay, that's different types of experiments. Those are still legitimate experiments, but then we have to calculate the binomial probability different. So now we're going to explore some more before we come up with this binomial probability formula. The grocery store gives away scratch-off cards if you purchase more than $100. Okay, that's excessive information. Okay, you're going to see that doesn't apply, but in word problems, sometimes they provide extra information. Now, the really important stuff. Terrell has 5 scratch-off cards. So we have a defined 5 trials. What's the probability that he has exactly 3 winning cards if each card has a 30% chance of being a winner? So first off, we need to figure out how many ways we can pick exactly 3 things out of 5. And we already know how to do that. So if you want to write down how you think you'll do that, great, you pause the video. If not, I'll give you the answer momentarily. So hopefully you said, okay, I know this is a choosing problem. Order doesn't matter. I just want to pick random 3 out of 5. So I got 5C3 is 10. Now some of you may have been a little bit more daring and said we could have winner, 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 loser, loser, and you could have winner, winner, loser, winner, loser, and you could write down all 10 possibilities and count that there's 10 different ways you can put 3 W's and 2 L's or whatever variables you use. Sometimes writing it out is a nice way to visualize. And then probability of a winner, okay, I call it S, P of S. Some people call it lowercase p. And probability of failure, we could write it as 70, well, it's definitely 70%. Some people write it as not success. Some people write it as Q. All interchangeable. We just really need to know the probability of winning and then the probability of not winning. In this case, I call it losing because you don't win. In this case, you lose. Now, all this is going to be useful and it's going to help us generate the binomial probability formula. So now, when I give you a formula, I always like to show you where it comes from. Okay, so down here is where I'm going to explain it, but a binomial probability formula helps us find the probability of winning exactly R times. Okay, it's not at least this many times or at most, it's exactly. So if I say I want to win exactly 3 times, I can calculate. So we're going to go back to that last problem. I want exactly 3 winners out of 5 tickets where there's a 30% chance of winning. We can compute the probability. Now here's the formula. We need a combination, and we're going to multiply by the probability of success however many times, and we're going to multiply that by the probability of failure however many remaining times. So we have 10 different ways. We already saw we have 5 choose 3 ways to pick 3 out of 5 winners. Now we want winner, 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 loser, loser. And this 10 is going to shuffle them up the 10 different times. So that's what this combination is doing to our formula. Now we've learned, and the reason why there's an exponent is it's repeated multiplication. Winner times winner times winner is, we just want winner to the third power. We want loser to the second power. So ultimately, we're just going to use this middle formula, but this is where it comes from. It comes from, we want winner, 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 loser, loser. We want to shuffle up and write and do it 10 different ways, so 10 times. But in math, we know that we can write stuff in a more efficient manner. Now, I can put that whole thing in my calculator, that whole expression. I can do 10 times 0.3 cubed times 0.7 squared. Any combination of how many steps you want to put in your calculator at once. For me, if it's multiplication and exponents, and we learned in the last lesson where the combinations button is, I'm doing that on my calculator. But you have the option to do every step by hand as well. Okay, it's a 0.1323 probability, which means it's about 13%. Now the problem will say round to the nearest percent or leave as a decimal. These generally are not written as a fraction, but they can be. So this is the formula, but you need to know that it's a binomial experiment first. This only works with binomial experiments. Please do not use this formula for everything and hope that it's always going to work. It only works in the specific case of I have a binomial experiment. So here's an example for you to try. Bag contains 5 balls, 3 green, 1 red, 1 yellow. You select a ball at random 4 times, replace the ball after each selection, calculate the theoretical probability of the event getting a green ball exactly 3 times, and I want your answer to the nearest whole percent. So pause the video. This problem should take a little while. And when you're ready, you unpause it, come back in, and you'll see the steps as I go through. And while I'm going through it, you can still pause the video and try if you make a mistake. Okay, so here's the first thing I always look at when I look at probability problems. What do I know about it? Okay, it's a binomial experiment. I either pick a green ball or I don't pick a green ball. I'm doing it 5 times. I know the probability of green ball. I like to write out my variables. I'm doing 4 trials. I want 3 successes. The probability of success is 3/5 or 0.6 if you wanted to do that. The probability that I don't pick a green ball is 2/5. And like I said, I like to use P and Q. Some people like to use success and failure, or they use P and 1 minus P. It is all the same. Now I can start constructing my formula. Probability of exactly 3. It says exactly. Okay, 4 trials, I want to choose exactly 3 successes. Probability of success, I want that to happen 3 times. Probability of not success, I want that to happen once. These exponents are always going to add up to the total number of trials. Okay, if I want 4 trials and I have 3 successes, I have to have 1 not success. And then I calculate that using my calculator. I don't expect you to do 3/5 cubed by hand. You can, but when we're doing this, the formula is super important in understanding what do we want to happen, and we have a 35% chance of getting exactly 3 balls, 3 green ones out of 4. Now, this problem could ask you to find exactly 2 or exactly 1, and we could use this to make a whole probability distribution if it said find the probability distribution of green balls out of 4 choices, and you'd have to find the probability of 0 and probability of 1 and 2 and 3 and 4. That would just be a lot of work. If you can find the probability of 3, you can probably find the probability of any other amount. So here is the challenge problem. Going back to Terrell and his 5 scratch-off cards. 30% chance of being a winner to the nearest 10th of a percent, what's the probability that Terrell has more than 3 winning cards? So I want you to think about this one, pause the video, try it out, think about what it's asking you to do, and do it. You can get this right, so try it out. Unpause the video when you're ready for me to explain or show the solution, and you can check. Okay, so once again, I always say it's a binomial experiment. Okay, you either win, you lose, it's 5 trials. Okay, but in this case, it says more than 3. So we can either have 4 winners or we can have 5 winners. And we're going to have to do each of these separately. So if you didn't do that, pause the video again, try it out from here. If that was the mistake, that's where the challenge was here. How do I deal with more than 3? There's no one formula that allows me to do 4 and 5 together. So I got to do 4, then I got to do 5 and find each probability, then we're going to add them. So I found the probability of 4. I find the probability of 5, and then I add these two to get more than 3, because those are the only 2 things that can happen to get more than 3. I can't have 6 winners and 5 cards. That doesn't make any sense. 0 winners is a problem. 1 winner is a problem. 2 winners is a problem. And since it says more than, not greater than or equal to 3, I can't include 3. So those are some of the challenges that I see. And some of the mistakes that students have made in the past is, well, they include 3 winners, but this says more than 3. So the probability of more than 3 winners, I add the decimals, I get 0.308, and I get 3.1%. Now, if it says round, okay, I'd write this as a whole lot of decimals. I wouldn't cut it short, because if you have rounding errors, that might cause you to have 3% or 3 point, well, probably just 3% in this case, if you cut off the 4. If you eliminated the 4s in both of them and then added, you'd wind up with 0.03, which is 3%. So no rounding errors. We can avoid those. We can do binomial probability. We can do multiple binomial probabilities and then add them together to get probability of more than 3 winners. So today, and in the last lesson, we learned the distributions. We learned a uniform distribution and a non-uniform distribution. We can write the probability distributions by finding the probability of each event. And then we extended that to the special case of binomial experiments and binomial distributions, where we know that the experiment can have 2 outcomes. We have to know how many trials we're doing, and each outcome is independent, or the probability of each trial is independent of every other trial. We also have the probability formula for the binomial probability. I'd recommend writing that down, highlighting in your notebook, circling it. Super important whenever we have a binomial experiment, that formula is probably going to be useful. And that's probability distributions.